Hello, wonderful algebra students. This lesson is going to be on connecting equations to graphs. Notice it is part 1, so we'll be starting this topic today and finishing it up tomorrow. The lesson, like I said, is connecting equations to graphs. We have spent the first 9 lessons of this unit so far spending a lot of time focusing on equations. We talked about how given a word problem or a scenario, how you can represent that with an equation. We talked about solutions to equations and what the solutions mean. We spent some time talking about equivalent equations and how even if you move around the parts to an equation, if you've got an equivalent equation, they're talking about the same thing. And then our last 2 lessons were on solving equations for a specific variable. A lot of that is going to help us in today's lesson as we look at connecting equations to graphs. If you had me for pre-algebra, we spent some time talking about graphs and pre-algebra. So you might want to reactivate that knowledge you have from pre-algebra to help you with today's lesson as well. So that objective is going to say, let's investigate what graphs can tell us about the equations and relationships they represent. So basically, why is a graph useful? What can I learn about the relationship from it? For our warm-up, we've got this question here that says, Jada has $20 to spend on games and rides at a carnival. Games cost $1 each and rides are $2 each. There are 2 parts to this question. The first one asks which equation represents the relationship between the number of games x and the number of rides y that Jada could do if she spends all her money. I'm just pointing out here that the x is the number of games and then y is our number of rides. So we've got 3 options there. Go ahead now and choose which one you think represents this equation. Pause the video and choose equation A, equation B, or equation C. For number 1, we want to go with equation C. If we know each game costs $1 and x represents the number of games, we could multiply the number of games times the cost of each game, which gives us 1 times x, or just x, to find the total amount of money spent on games. Similar process for the number of rides. We're going to multiply the number of rides times the $2 per ride to get 2y. And then together, or that total, should equal $20. She's spending a total of $20. Now that we are in agreement that equation C is the equation that represents this situation, equation A and equation B are still equations. And they might not represent this situation, but they could represent a different situation. So in number 2, that's what we're going to do. We are going to explain what these other 2 equations could mean in this situation of games and rides. They don't represent this description here in number 1, but they do represent something. What is that? Go ahead, pause the video now and try number 2. Well, looking at equation C and equation B, they're pretty similar. That 2 is just moved. You can use your description of equation C to help you come up with a description for equation B. Equation B just has those prices flipped around. If we've got 2x, that means we're multiplying the number of games, x, by 2. That would mean that each game costs $2 in this situation. And then that y there's that 1 in front of that y. That would mean those number of rides, y, we're multiplying it by 1 because in this situation, each ride costs $1. And then that still equals 20. So we could still say, and Jada spends a total of $20. That part hasn't changed. The last part there is also going to be similar for equation A. Difference in equation A is we've got x and y by itself. We're not multiplying them by anything, or you can think of we're multiplying them by 1. So in equation A, we've got each game costs $1 and each ride costs $1, and Jada is still spending a total of $20 there. Notice those descriptions are similar to that description we have for C. The difference is in equation C, each game costs $1, each ride costs $2, and she's spending a total of $20. Before we leave our warm-up, I want to point out something about these three equations. When we look at these three equations, notice they all are in a similar form. We call this form standard form. What standard form is any equation with two variables, which all of these have two variables, x and y. Any equation with two variables that is in the form ax plus by equals c, where a, b, and c are all numbers, and x and y are just x and y. Looking at these three equations, notice that for every single one of those equations, on the left side of the equation was our x and y, just like here in standard form. And then on the right side of the equation was a number. And the number we represent as c. Each of these equations, therefore, are in standard form. When equations are in standard form, it gives us some helpful information. Looking at these three equations here, because they were written this way, what were you able to learn about each of these situations? It might help to look at some of those observations you made in number 2, or think about how you were able to match the description in number 1 to the correct equation. Well, the benefit of standard form is what we're able to learn from equations when they're in standard form, which in this situation with games and rides has to do with the prices of everything and the amount of money she spent. For each of these equations here, notice we were able to learn two things just by looking at the equation. We are able to learn the unit cost of each game and the unit cost of each ride. So one of the benefits here of these equations being in standard form is we were able to learn the unit costs of games and rides. We were also able to see that for each equation it equals 20. The fact that it's in standard form when we can see it equals 20 helps us know how much total money she has to spend. So we also were able to say, I know the unit cost of a game, the unit cost of a ride, and the total amount of money spent. These are all benefits of having these equations in standard form. For our main activity we're looking at today, we're going to be looking at equations in standard form and also equations that are rearranged and no longer in standard form. So it could be helpful to think through, like, why is it helpful to have these equations in standard form? With that, we will move down to activity number 2, which is where we're going to be focusing in the rest of our time. In number 2, we are going to be looking at more games and more rides. These you can think of are maybe different carnivals. So not the same carnival we were talking about earlier with x plus 2y equals 20, but similar in the sense that each represents a relationship between the number of games x and the number of rides y, and the dollar amount a student is spending on games and rides at different amusement parks. So notice here we've got 3 equations. Similarly to what you were doing earlier, think about what do each of these equations tell you. Go ahead, pause the video and think through that now. Well, notice equation 1 is one of the equations we had earlier. That was equation A from earlier. So this equation is telling me each game cost $1, each ride cost $1, and that student is spending a total of $20. Equations number 2 and 3 are different, but that description is going to sound really similar. That 250x is telling me that each game costs $2.50. The y by itself tells me each ride costs $1, and this student here can spend a total of $15. In equation 3, we've got that each game costs $1, each ride costs $4, and this student here can spend a total of $28. Being able to interpret these questions like that is going to be important for the math we're doing today. Now, we've got 3 equations. I've actually changed around the order a little bit. I'm going to be going through equation 3 together with you right now, and then I'm going to give you an opportunity to try equations 1 and 2, which are going to be very similar to what we did here on your own. So starting with equation 3, x plus 4y equals 28. Number 1, the first question we want to answer is what is the number of rides the student could get on if they don't play any games? If this is describing the money you have and the cost of games and rides at the amusement park you choose to go to, how many rides could you get on if you do not play a single game? Think through that now. Well, if you are not playing any games, remember X represents the number of games. If you were not playing any games, that must mean that X, or the number of games you play, equals 0. If you were not playing any games, that means you are spending all of your money on those $4 per ride. I can use this equation to help me think through this question by saying, well, if you are not playing any games, X must be 0. And so you are just paying and playing $4 per ride with your total of $28. We go to solve this equation, we're going to get that Y must equal 7. If you do not play any games, you can go on a total of 7 rides. We are going to be connecting this equation to a graph. So I want to represent what we just found on our coordinate plane down here. Here is a coordinate plane showing the number of games and the number of rides that the student can go on. We just found that if you don't play any games, you can go on 7 rides. If I mark that information with a point somewhere on this coordinate plane, where would that go? No games. If you play no games, you can go on 7 rides. Well, no games would be here 0 at our number of games. If I play 0 games, I can go on 7 rides. That 7 would be this point right here. This point represents a combination or a pair of 2 numbers. That pair of numbers is 0 games, so 0 for X, and then 7 for Y, or 7 for the number of rides. We're going to do something similar in number 2. Go ahead, pause the video now and try number 2. Well, this time in number 2, it says the number of games the student could play if they don't get on any rides. So now it's reversed. This time we've got they're not going on any rides. That means that Y, my number of rides, must equal 0. I can do that same thing I did before. I can take my equation. Let's try that again. I can take my equation X plus 4Y equals 28. And I could say, well, if we're not going on any rides, Y must be 0. And when I go to solve that, I'm left with X equals 28. That means if that student doesn't get on any rides, they can play 28 games. Similarly for this first part, let's represent this as a point on my graph. We've got, if they don't go on any rides, they can play 28 games. On our graph, we're going to say they can play 28 games and go on no rides. That would be this point here, which is at 28 on my x-axis and 0 on my y-axis. Notice I didn't go up or down. So we've got that right there as my second point. Now, one of our goals with these problems is I've given us an equation to look at. We want to represent this with a graph. Remember, the whole purpose of this lesson is connecting equations to graphs. Once I found these two things, once I found how many rides I could go on if I play 0 games and how many games I can play if I go on 0 rides, that gives me 2 points on our line. In order to graph a line, you need 2 points. Well, I've just found 2 points, so I can go ahead and graph my line. I can graph my line by coming in here and drawing, not like that, but drawing Y. There we go. I was being too fast. Drawing a line between those 2 points, like that. Quick check to make sure we understand what this graph is saying. I'm just going to pick a random point for us. Let's pick this point right here. What is that point telling us in this situation? Well, that point is telling us that this student can play 12 games and go on 4 rides. And because it's on the line, it means if they go on 4 rides and play 12 games, they're spending that total of $28. You could also pick a point off the graph, like this right there. That point's still representing a combination of numbers. It's representing 22 games and, 22 rides. Because it's not on the line, it means that would not be $28. It would be more than the money she has. Coming back to our problem here. So at this point, we figured out these 2 points. We've plotted those 2 points on our graph, and then we've graphed this line here. These last couple questions are to help us think through another way you could think of this graph here and connect it to equations. So number 4, we're going to complete this sentence here. It says, if the students played no games, they can get on how many rides? What do you think? If they played no games, that's 0 games, means they can get on 7 rides. We already found that point earlier. We've got no games means 7 rides. After that, for every additional game that a student plays, remember number of games is X, the possible number of rides, Y. Let's pause here. Does it increase or decrease? So a different way to think about this is we're starting off here, no games, you can go on 7 rides. If we decide, okay, well, there's 1 game I want to go on, what's that mean in terms of the number of rides you can go on? Does the number of rides increase or decrease? The number of rides decreases. The more games I go on, I keep saying go on games, the more games I play, the less rides I can go on. There's a number we can put with that. For every 1 game I play, what's that mean about the number of rides? How much is that going to decrease by? Well, if we look at our graph here, if I went on 1 game, I can see the number of rides has decreased, but it's not quite clear what it is. We might be able to do some math to help us out. I can see if I go on 4 games, that's easier to see. I can see I've gone down 1 ride. So after 4 games, it's gone down 1 ride. Figure out what that means for each game. After 4 games, it's gone down 1 ride. It means after 1 game, it's gone down 1/4, or that could be 0.25. So you could think of it as 0.25 or 1/4, whichever one you prefer. That's also going to come up in this next question, number 5, which asks us to calculate 2 things. The first one is, what is the slope of your graph? And then the second one is, where does the graph intersect the vertical axis? Let's start with this part here on slope. If you had me for pre-algebra, you know we talk about slope a lot back in pre-algebra. What is slope? What do you remember about slope? Do you remember how to calculate slope? Do you remember what it tells us? Pause the video here and kind of think through what you remember. Some of the things we had learned about slope is that slope is a number that tells you about the direction of the line. One of the things we had learned with slope is it depends on if slope is positive or negative. That tells you something about the direction of the line. If the line is going up or down. And then we learned that number is telling you how much the line is changing, or the direction is changing over time. We had also talked about when you're calculating slope, to calculate slope, you need to use rise over run. Rise over run is the formula we use when we're calculating slope from a graph. Notice a moment ago, that's exactly what we were doing. We were calculating the rise. We noticed that if that line goes down 1, your rise is that change vertically. The run, how much that line goes over, it goes over 4. So we've got our slope is negative 1/4, or if you divide that out, that gives you negative 0.25. Notice, does that look familiar? I hope it does, because we just did it right here. We found that earlier, as you play 1 more game each time, the number of rides decreases by 1/4, and here we were getting a negative 1/4. What about where that graph intersects that vertical axis? Well, if I follow this purple line right here, where does it cross our y-axis? That's nice and easy to see. Just find your y-axis, and where this purple line here crosses it, it crosses right there at that blue point we had calculated earlier, which is at the number 7. So notice we've got our slope is negative 0.25, and then we've got that vertical axis, or that y-intercept. That point right there is at 7. There's one last thing we're going to do, and that is that earlier equation we had, where we've been getting all these numbers from, that equation right here, x plus 4y equals 28. Let's go ahead and practice our solving skills. We're going to take that equation and we are going to solve for y. So I'm taking that equation, x plus 4y equals 28, and I want to solve that equation for y. Solving an equation for a specific variable is something we were learning in lessons 8 and 9 yesterday and on Thursday. So I encourage you, pause this video now and see if you can solve this equation for y. All right, if I want to solve this equation for y, I'm trying to solve for y. That means I need to get y by itself. I need to isolate y. In order to do that, we always start with our constant, which is that number that's added or subtracted. And in this situation here, that constant is x. Because it says plus x, I need to do the opposite. And the opposite of that would be subtracting x. So I'm going to come in and subtract x on both sides. When I do that, that leaves me with 4y on that left side. I just have 4y because x minus x, that's like 1x minus 1x. That's 0. That's nothing. Those cancel out. So we get 4y on that left side. On the right side, you can't subtract a number in a variable, so we just have 28 minus x. Now we are not done solving for y because we still have that 4 in front of it. Our last step, if I'm trying to get y all by itself, because 4y means 4 times y, it means multiplication, I need to do the opposite of that, which would be division, and I want to come in here and divide by 4. When we talked about solving equations for a variable and equivalent equations, we talked about how when you're doing something like multiplying or dividing, it's important you do it on both sides. And I'm emphasizing that word side here because if I divide this left side by 4, I need to divide the right side. And notice that division line is going across the entire side. I'm dividing that right side by 4. Now when we do that, those 4's, 4 divided by 4 gives me 1, so we get 1y, or just y. And then on our other side, if I wanted to divide that out, I could say, well, 28 divided by 4 gives me 7. When I go to divide my x by 4, notice there's no number in front for me to divide, but we know what number is there. That hidden number right there is 1. If you do 1 divided by 4, that gives you could write 1/4 x. I'm going to go ahead and write that decimal 0.25x. But if you had gotten 7 minus 1/4 x, that's an equivalent equation, so that's the same thing. So we get the equation y equals 7 minus 0.25x by rearranging this original equation we had there. This point, we're going to pause and do some observations and reflections. Do you notice any connections between this equation here and the math and the graph we did in numbers 3, 4, and 5? We got the equation y equals 7 minus 0.25x. Here's our graph and our answers for 4 and 5. Go ahead, pause the video now and see if you can find any connections there. I think number 4, in terms of what those numbers mean, is going to show us the biggest connection. Notice when we solved for y, we ended up getting those same exact numbers we've been looking at in numbers 4 and 5. We've got 7, 7, 7, and I've got that 0.25, 0.25, 0.25. I didn't see those numbers in that original equation, but once I solved it for y and rearranged it, we can see in that equation that 7, which we had said earlier, is that y-intercept, or that point where if you do not play a single game, you can get on 7 rides. And we're also seeing that 0.25, which remember earlier we said that 0.25 represents as you play another game, the number of rides is decreasing by 0.25 or decreasing by 1/4, which happened to be the slope earlier. This is not a coincidence we are seeing all these numbers for these same questions here. When we rearrange this equation for y, you are going to see those two things, the slope and that vertical axis or that y-intercept. So it's all connected. To kind of help us to practice with these skills and emphasize that connection, there are two other equations, remember. So I did equation 3. I'm going to strongly encourage you to pause the videos and try equations 1 and 2. I'll come down. I'm doing everything backwards for this video. I'm going to have you start with equation 2 first. So this is the equation. These questions here are all the same questions we had just answered for that earlier example, I guess, just with a different equation. So I'm going to strongly encourage you, go ahead, pause the video now. This is your equation to try, and then you want to answer questions 1 through 5. Okay, gone ahead and done numbers 1, 2, and then got our graph here. For number 1, if you want to find how many rides you can go on if you don't play any games, we aren't playing any games. That means that x, or our number of games, equals 0. In order to answer that question, substitute x equals 0 into this equation, and you're going to get y equals 15, or that you can go on 15 rides. We've got that represents this point right here on our y-axis. Similarly, for number 2, if we want to find how many games you could play if you don't go on any rides, if you don't go on any rides, that means y, or the number of rides, is 0. Just like before, to figure out how many games then, you could substitute y equals 0 into this equation, and when you solve, you get 6 games. Just like before, that represents a point on that line, so that gives us our second point here, and then we are able to draw the line. If you had a different equation, a different graph, different information, that would have impacted your 3, 4, and 5, so I encourage you to go ahead, pause the video, see if you can fix 3, 4, and 5. If you had this and you've got 3, 4, and 5, then just keep watching the video. All right, I've gone ahead and I've got the answers up for 3, 4, and 5. For number 3, if the student played no games, based on our graph, it's real easy to see. No games means 15 rides. It's that first point we've got there. What's not as easy to see is for the second part, which says for every additional game that a student plays, x, the possible number of rides, y. What we can see is if you play more games, that means you can play less rides. I see that because I see that line is going down, which tells me it's going to decrease. But that 2.5 there, we might take a guess. Like looking at this, it looks like maybe we're starting here at 15, so like maybe 2 or 3 to go over 1. But what I ended up needing to do to be confident in that 2.5 is some calculations, which leads us to this next part here with the slope. In order to calculate slope, remember we said slope is rise over run. In order to calculate your rise over run, you can pick any 2 points. For this one here, I ended up picking that y-intercept and x-intercept and said, well, looking at that, I'm going down 15 over 6, down 15 over 6, ends up equaling negative 2.5. But you don't have to pick those 2 points. If you recall earlier, we picked this first point here, that y-intercept, and this point. I could have done the same thing using that y-intercept and x-intercept. No matter which 2 points you choose, you're going to end up getting the same slope, which for the second one here happens to be negative 2.5. The other question in number 4 asks, where does the graph intersect the vertical axis? This graph here intersects at 15. So notice again, we're seeing that 15 and that 2.5. I've got 15 and 2.5. The last part was rearranging this equation to solve for y. We've got that original equation there. I subtracted that 250x from both sides to get y all by itself. I'm subtracting because that original equation says we're adding 250x, and I need to do the opposite to solve. So we're left with y equals 15 minus 250x. Again, notice I've got that 15, I've got that 250 earlier. 15 and 2.5, 2.50 are the same number. So it's all connected. But how is it connected? How does this new equation here How does that connect to this graph? That is the ultimate question we're trying to answer. There's one last one for you to try. So that last equation is x plus y equals 20. Just like before, all the same questions. Go ahead and pause the video. I encourage you really truly pause the video and practice this question here now. Alrighty, and this is me checking in. If you're unsure where to start, notice I jumped right into graph this equation. In order to graph this equation, just like in these past ones, we want to find that y-intercept and that x-intercept. How have we been doing that in each of these problems? Well, every single time we've used this idea of substitution and substituting in 0 for one of those variables to find that other value. So to find that 7 in that first problem, we substituted x as 0, and then we got 7 rides. Similarly, to get that that x-intercept of 28, we substituted in y equals 0 to get 28. You're going to have to start this off by using some substitution. Here's our question. Okay, so if you're struggling to get started, that's my hint. Go ahead and continue on. We'll pause the video and then continue on the work. All right, and here are the rest of the answers. Notice up here, use that idea of substituting 0 for both x and y to find those two intercepts. When I substitute x for 0, I got y equals 20, which would represent this first point here. And then when I substituted y as 0, I got x is 20, which is this other point right here. That gave me my line. From that graph, I can see that if the student played no games, that would mean they could go on 20 rides. And then for every additional game that the student plays, so as we add in more and more games, the number of rides is decreasing. It's decreasing by 1. Out of all of these, I think this is the graph that's easiest to see. I can see when I found my slope, I see that if I go down 2 rides, it's going over 2 games. So from that, I can conclude that every single game they go on, 1 more game means 1 less ride. The last part was me rearranging this equation to solve for y. We do that by subtracting x on both sides, and we get this equation y equals 20 minus x. So at this point, we've looked at 3 different equations, 3 different graphs, a whole lot of questions. What does it all mean? I'm going to switch this over to, here you go, this document here. On the top part, we've got those 3 equations, which we learned in today's lesson. Those are all called standard form. That capital T is going to bother me. We got standard form here of those 3 equations. We've got the graphs that we came up for each of those equations. And then we've got these rearranged equations that we found by solving for y. Notice that for each of these rearranged equations, I ended up putting x first and the number second. That is so that it falls into the second form we have, which is slope-intercept form. Slope-intercept form looks like these equations here, but it's in the form y equals mx plus b. You might know what m and b represent based on some of those observations you made. For example, let's look at this first one here, which is it's the last one here, but the first one we had looked at together, that negative 0.25. Do you remember what that means? Well, that was our slope. And then the b, that's 7. Where do we see that 7 on the graph? Well, that 7 was this point right here. That was our y-intercept. So this what we're looking at right now is pretty much a summary of what we ended up doing in this lesson. I gave you these original equations in standard form, and you, for each of those equations, graphed them, and then you solved those equations for y. Some questions that I want to talk through here at this point. each time we were solving for y. And we had said there's a reason we would solve for y. There's a way we can connect these equations here to the graph. Do you see how they're connected? Do you see how they're related? Well, they're related in a few ways. Notice that each time that number, that constant, the 20, the 15, the 7, that ended up being our y-intercept each time. And then the slope, first of all the slopes are a negative number. That's telling us that that line is decreasing or falling as you go from left to right or as the number of games increases. And then that number tells you by how much. So we saw in this most recent one we did that -1 is telling me that every single time you play a game, it means the number of rides you can go on decreases by 1. For the second one here, every single time you play a game, it means the number of rides you can go on decreases by 2.5 rides. For that last one, every game you play means the number of rides you can go on decreases by 0.25 rides. So all those slopes there are describing that relationship specifically between rides and games, and kind of this idea of like the trade-off between those two. If we play a game, it means less money for the ride, so we know that the number of rides is going to decrease, but by how much? That's what those slopes there are telling you. As we look at these 3 problems as well, each of them we represented with 2 equations. What are your thoughts on those 2 equations? Are they different? Are they the same? Do they describe the same situation or the same scenario? Do they describe different scenarios? What do you think? Well, remember how we got these second equations. We got these second equations by rearranging this first equation. Because they're coming from rearranging the standard form, means these equations down here, which are in slope-intercept form, are an equivalent equation to these first ones. You can rearrange an equation to get an equation that looks different. These equations certainly look different, but they represent the same scenario. That means if I gave you this equation and asked you to graph it, or if I gave you this equation and asked you to graph it, they're both going to look like the same graph because they're ultimately describing the same relationship. So then that kind of begs the question of why would we want to do this? If they represent the same relationship, what's the benefit to having the equation in standard form versus what's the benefit to rearranging it in slope-intercept form? Earlier, we had talked a little bit about what the benefit of standard form is. Do you remember what we said that benefit is? Well, for standard form, remember at the very beginning of all this, I gave you these equations and I asked you, what do they mean? What do they tell us? And we had figured out one of the benefits of it being in standard form is it tells you that unit price. This one right here is telling me that each game costs $1, each ride costs $1. This equation here tells me each game costs $2.50, each ride costs $1. This last one tells me each game costs $1, each ride costs $4. So the benefit of standard form is it's telling you that unit price. It's also telling you how much total money that the student has. This student in this last one had $28 versus the student in the first one only had $20. We're able to get all of that information just by looking at standard form. When you look at the slope-intercept forms of those equations, it doesn't give us that same information. I think that's really clear with this last one here. I can't see, if I'm just looking at this equation, that that student had $28. I can only see that information in standard form. Slope-intercept form, though, isn't useless. It just tells you different information. What's the benefit of looking at the equations in slope-intercept form? Well, the benefit has to do with the name of the form. Notice slope-intercept is the name of the form. The benefit is it tells us those 2 things. Let's start with the intercept. In each of these slope-intercept forms, notice that it's telling us that y-intercept. And again, I really want to focus here on this last one. That y-intercept was 7 and look at our graph. That y-intercept there is 7. Again, that number 7 isn't a number I see in that original equation in standard form. It's something we only discovered once we rearranged the equation and solved for y. The other thing that these equations tell us that standard form doesn't is the slope right here. Remember what we had mentioned about slope. What does slope tell us here? Well, it tells us how adding more games affects the number of rides. For example, with this first one, that slope being -1 tells us that for every additional game you play, it means the number of rides is decreasing by 1. If I end up deciding, well, instead of just going on 20 rides, I want to play 3 games. If I increase the number of games I'm playing by 3, it means the number of rides is decreasing 1 per game, so it would be decreasing by 3. So the slope here, I'm going to use that word trade-off again. That slope is really telling you the trade-off between rides and games. It's telling you about that relationship between the two of them, and if one of them increases or decreases, how it affects that other one. Again, that idea isn't present in standard form. That number we had calculated each time, we can only see that number in slope-intercept form. So remember, the purpose of this lesson was ultimately connecting all this work we've done with equations to graphs. Remember, there is a part 2 coming up. But one of the things I really want you to leave this lesson with is this idea of why. Why we would want an equation in standard form and why we would want an equation in slope-intercept form, and what you can learn from each of them. That's going to be a really big theme as we look at more and more graphs. That is everything I've got for this lesson. Thanks so much for watching, and I will see you again tomorrow for part 2 of connecting equations to graphs.